Have you ever heard of the Tachyon paradox, a mind-bending puzzle in physics where faster-than-light or FTL particles seem to break causality? In simple terms, if you send a tachyon signal in some reference frames, it looks like the message is received before it's even sent. This leads to famous contradictions, like the grandfather paradox where cause and effect collapse. But in my research, I propose a fresh solution, the second clock hypothesis. This framework introduces a dual time model, two distinct timelines running side by side. The first clock, T1, governs everything we know, normal matter, subliminal speeds, and all classical events. The second clock, T2, is reserved only for superluminal processes, tachyons, hypothetical FTL communication, and similar phenomena. Now here's the key insight. It's not time itself that bends or breaks. Instead, a clock or a watch is just a device that slows down or speeds up, depending on the environment, whether in motion or under gravity. Time itself in the background remains universal and uniform. That's why when we introduce a second clock dedicated to FTL phenomena, paradoxes vanish. Let's look at the classic setup. Observer A on Earth sends a tachyon signal to observer B, who's on a spaceship moving at relativistic speed. In relativity, B might appear to receive the message before A sends it. If B responds with another tachyon, the reply could get back to A even earlier, forming a causal loop, a paradox. But with the second clock hypothesis, all tachyon events are confined to the T2 timeline. A sends the signal in T2, B receives it in T2, and if B replies, that too happens in T2. To someone looking from T1, it may look like messages are going backwards in time, but that's just an illusion. Since tachyons never evolve along the T1 clock, they never interfere with the cause and effect chain of normal physics. The conclusion is powerful. By separating subluminal and superluminal timelines, the tachyon paradox dissolves. Causal loops can't form because the clocks themselves are distinct. The second clock hypothesis keeps T1 consistent while giving T2 its own domain. This way, faster-than-light processes can be described logically, without contradiction. In short, time itself doesn't slow down, clocks do. And by introducing a second clock for the superluminal world, we finally have a clean resolution to one of physics' most puzzling paradoxes.